Hello friends, welcome to my channel. In this video, I will explain single phase transformer. In this slide, I have shown four different images. In the first figure, I have shown transformer which are used for electricity distribution purposes. In the second figure, I have shown internal structure of DC voltage regulator. It is actually adapter in which there is a transformer. Third image is of internal structure of mobile charger in which there is a transformer. And in our laboratory, we are using transformer, and that I have shown in fourth image. Now let's discuss what are the uses of transformers. Very basic and fundamental use of transformer is to change AC voltage level. We have to either increase AC voltage level or decrease AC voltage level. So in that case, we have to use transformer. Apart from that, there are so many uses, such as transformers are used in power generation, transmission, and distribution purposes. It is used as a circuit breaker. It is also used for isolation between two different circuits. And suppose I want DC voltage supply. In that case, I can convert my AC voltage into the DC voltage. In that case, the very first stage is to either reduce the AC voltage or to increase the AC voltage. So in that case, we can use transformer. Now let's discuss construction of transformer. At the center, there is a core which is shown with a gray color. And there is a provision to wound coils on two different limbs. Coil means it is an insulated copper wire which is wounded around limbs. On two opposite limbs, there are two different coils are wounded. From one of the coils, we are going to apply the voltage V1, which is a input voltage. And that coil will be referred as primary coil. And we are going to get output from the other coil, which will be referred as a secondary coil. And voltage will be referred as a V2 voltage. So V1 is the input voltage, V2 is the secondary voltage. V1 is also called as primary voltage and V2 is also called as secondary voltage. N1 and N2 are the number of turns at the primary side and secondary side respectively. N1 and N2 ratio will be playing important role for deciding output voltage. In case N2 value is greater than N1, then output voltage will be greater than input voltage. If N2 is smaller than N1 value, then output voltage will be smaller than input voltage. Ratio of output voltage upon input voltage, that means V2 upon V1, is also called as transformer ratio. So based on transformer ratio, that is ratio of V2 and V1, there are two different types of transformer: step up transformer and step down transformer. The transformer which increase the AC voltage level, which is called as step up transformer, whereas the transformer which reduce the AC voltage level, that is called as step down transformer. Based on type of core, there are two different types of transformer. First one is a core type, second one is a shield type. The structure is shown in the figure. These are symbols of the transformer. In first, I have shown iron core type transformer. If core is consisting of iron, then we have to show two vertical lines. If our transformer is not having iron core, it means if it is an air core, then we do not have to show vertical line. Now we will discuss derivation of EMF. In figure 1, I have shown electrical transformer. At the left side, there are primary windings, and at the right side, there are secondary windings. At primary side, we have to apply V1 voltage, which will be alternate voltage. And at the secondary side, we will be getting V2 output voltage. When an alternating voltage V1 is applied to the primary coil of the transformer, an alternating current I1 flows through it, producing alternating flux in the core. This flux links with the primary winding, and according to Faraday's law of electromagnetic induction, an EMF E1 is induced in the primary coil. The value of E1 is given into the next slide. Almost all flux produced by primary windings links with the secondary winding, hence an EMF E2 is produced into the secondary coil. The value of E2 is given into the next slide. EMF induced in primary coil is given by minus N1 multiply rate of change of flux. Flux is not constant, it is changing according to the applied V1 voltage, and that's why flux is also alternating flux. So we will keep value of flux, that is phi is equal to phi m multiply sine of omega t in the above equation. And if we take derivative of phi m sine of omega t, then we will get E1 value is equal to minus N1 into omega into phi m multiply cos omega t. We will convert this into the standard sine FM equation. So my new equation will be E1 is equal to N1 multiply omega multiply phi m multiply sine of omega t minus pi by 2. Now here coefficient of sine term, that is N1 multiply omega multiply phi m, will be giving us maximum E1 value. So in this slide I have shown E1 max value is equal to N1 multiply omega multiply phi m. So we can substitute value of omega is equal to 2 pi f, and that's why E1 max is equal to 2 pi f into N1 multiply phi m. We can find out RMS value of E1 by dividing max value by root 2. So new value of E1 is equal to E1 max divided by root 2. If we substitute value of pi is equal to 3.14 and so on, then and if I simplify the value of E1, the simplified answer will be E1 is equal to 4.44 into f into N1 multiply phi m. Similar thing I can apply for E2 also, and I will get E2 equation is equal to 4.44 f into phi m. Ratio of E2 upon E1 is called as transformer ratio. So if we simplify it, then we can get this equation. So E2 upon E1 will be equal to N2 upon N1, which is indicated by K, which is also called as transformer ratio. Now let's discuss losses into the transformer. Broadly, there are two categories of the losses: iron loss and copper loss. Iron loss is also called as core loss. Again, there are two types: hysteresis loss and eddy current loss. Now let's discuss copper loss. In ideal case, we are saying that copper doesn't offer any resistor, but in actual case, copper is offering certain amount of resistor. Here in this figure, I have shown resistance offered by primary windings is given by R1, whereas resistance offered by secondary winding is given by R2. Let's say we have applied V1 voltage at the primary side, and because of that I1 current is flowing through primary coil. At the same time, I2 current is flowing through the secondary coil. We know that power consumed by any resistor is given by current square multiply resistor value. And that's why copper loss due to primary winding is given by I1 square multiply R1. Similar way, copper loss at the secondary side is equal to I2 square multiply R2. So total copper losses is given by power loss due to primary coil and power loss due to secondary coil. Now next is core losses. In core losses there are two categories: eddy current losses and hysteresis losses. Now let's discuss eddy current losses. We are applying alternate voltage at primary coil of the transformer, because of which alternate flux will be created. And because of this alternate flux, alternate current will be circulated through core, which is called as eddy current. Because of this eddy current, there is certain amount of loss which is called as eddy current loss. The formula for eddy current loss is equal to K multiply V max multiply F square multiply T square into V, where V max is a maximum flux density, F is a frequency, T is a thickness, and V is the volume. To minimize eddy current losses, we have to use laminated thin layers of iron sheets. Now move on to hysteresis losses. Alternate voltage at the primary causes constant movement of molecule in the transformer core. This leads to dipole change their directions continuously, and because of that collision will occur. Hysteresis loss is given by neta multiply B max into F into V. To reduce hysteresis losses, we have to use high permeability material for core such as ferromagnetic material. Now efficiency of the transformer. Due to losses into the transformer, output power is always less than input power. Efficiency of transformer is defined as ratio of output power upon input power. As we have seen, there are different losses. That losses we have to include in our formula of efficiency of the transformer, and that's why efficiency is equal to output power upon output power plus iron losses plus copper losses. We have to mention how much is the iron losses and copper losses, and that's why formula which we can write as V2 into I2 into cos phi 2 upon V2 into I2 cos phi 2 plus Pi plus I2 square into I resistance. Meaning of each notation is given in this slide, so you can go through it. And here I have compared ideal transformer with the practical transformer. As we have seen, when we are comparing ideal transformer with practical transformer, we have to assume that in ideal transformer there is no any kind of loss into the transformer, whereas in practical case there is always certain amount of power loss. So first point is, in the ideal transformer it is a theoretical model of transformer with no energy losses in it, whereas in practical transformer there is always certain amount of loss. Second point in the ideal transformer is there is no leakage of flux, whereas in practical transformer there is always certain amount of leakage flux. Third point in ideal transformer is its winding consists of purely inductive coils wound on lossless core, whereas third point in practical transformer is its winding contains ohmic resistor. Fourth point in ideal transformer is efficiency is always 100%. This is the ideal case, but in practical case there is always less than 100% efficiency. So efficiency is around 93% to 100%. Last point about ideal transformer is it is impossible to construct an ideal transformer, whereas last point in the practical transformer is all constructed transformers are practical transformers. So thanks for watching my video.